allowed around about now. Okay, hello and welcome everyone. Welcome to the webinar. I'm going to talk about blockchain and try and tell you everything you need to know about blockchain, or at least an introduction, in 50 minutes. So I will just share that. Have a look at just. I'm just quickly going to bring up the participant list. Okay, Tanya, I'm just going to mute your microphone there. Okay, so hello and welcome everyone. So blockchain in 15 minutes. So what you can think about is that you have information that you want to update, and that information is encapsulated into a transaction. So maybe the transaction is, I will send you money, but it could be something far more complicated. I will update the state of something. I will change some record. And so in blockchain speak, they're called transactions. And you group transactions into something called blocks. And then blocks are linked in chronological order to form a chain. And for instance, as you're seeing in this slide. So updates can only be added to the end of the chain. You can't add information in the middle. So for instance, with here, you can add that red block at the end, but you couldn't say alter the inside of the block earlier on. And if someone tried to do that, you would be able to detect it. And so you can think of the blockchain as a general ledger. It's a way of, say, it's similar to how you used to track financial transactions in, say, a big ledger book like the one here. And you never cross out anything in the middle. You only ever write things at the end. And so as an example, you could have a land registry office record showing who owns what land. And you could have someone who buys the land, say, in 1857, and then it's sold and then sold again and sold to the current owner. And doing those changes, you're updating the record, but you're writing new values in, new lines into the registrar, but you're not crossing out the old ones. And so, it's a non-destructive way of adding things to the end of the record. And so with these ledgers, so in the good old days, they were paper. And then in the 50s, 60s, 70s and 80s, they all moved towards being centralized computer databases. And so you computerized it, but still you had a central database of information. And so with blockchain, you've got a decentralized database. So the blockchain, you don't have all your data in one spot. You've got multiple computers which are operated by multiple entities. So they could be completely different organizations, completely different organizations in different countries. One could be operated by an individual. Or maybe if it was a private chain, maybe you've got different business units within the one company or different groups. So maybe you've got finance, sales and engineering. They each are on the same blockchain, but they've each got different nodes. And so the idea is that you've got multiple copies of the database are distributed across the computers. And so say if one of the nodes, one of those computers, say the network connection stops, or the computer itself stops or is corrupted, or if you have a malicious attacker takes it over, then the rest of the computers on the network, then the rest of the nodes on the network will be able to use algorithms to determine that that version of the database is wrong, and that they'll come to a consensus, come to an agreement on what the true version is. So consensus is the process by which a network of computers come to an agreement. And so each blockchain has its own way of coming to consensus. So each has, there are many different algorithms. And so one of the main types of algorithms is called proof of work. And so you have different nodes in the network, which are miners. And each of the miners is racing to try and solve a cryptographic puzzle problem. And whoever solves that puzzle, that mathematical puzzle first, they get to create the next block. And so it's a way of fairness, that it's mathematically shown that the probability of producing the next block relates to how much effort you put into solving the puzzle. And so because of that, you end up with things like what you've got in that photograph there, where you've got whole factories worth of computers busily trying to solve the cryptographic puzzle. And so Bitcoin and Ethereum mainnet use that sort of consensus algorithm. Proof of stake is a way of coming to consensus where validators stake an amount of money, and then using a random selection algorithm, you work out the validator that's going to mint the next block. And so when you're doing that, you could just do it on a laptop computer. You don't need a factory worth of computers. And so newer blockchain systems are trying to work out good proof of stake algorithms that are guaranteed to be fair and aren't corruptible. And so Ethereum 2, so the next version of Ethereum, is looking at using that. You've got proof of authority algorithms. So these algorithms, you rely on all of the participants being known, and the validator that's going to create the next block is chosen based on a certain algorithm. So you do round robin. So one party gets it, then the next, and the next, and the next, then back to the original party, or some other fairness mechanism. And again, that type of consensus does not need a factory worth of computers. It just works on a single computer and for each node. And so they're useful for consortium blockchains or private blockchains between a set of companies. So for public blockchains, you've got Bitcoin, which allows you to transfer value, and you've got Ethereum mainnet. You can transfer value, and you can do something called smart contracts. And so smart contracts are essentially computer code inside of the blockchain, which allows you to do business logic. There are also private blockchains or distributed ledger platforms. And so Pantheon, which is an Ethereum-based one, is one that actually the group that I work for in developing or have developed. There's Quorum, which JP Morgan have created. And there's Hyperledger Fabric, which IBM created and then donated to Hyperledger Foundation. So they do things in slightly different ways, and there are slightly different properties, but they all work on essentially proof of authority style consensus algorithms. So if you try and compare and contrast the public and consortium blockchains, so the consensus algorithm, for public, it's going to be proof of work or proof of stake, whereas consortium, it's proof of authority. From a centralization standpoint, public blockchains are more decentralized, whereas consortium blockchains are generally less decentralized, or maybe partially decentralized, because essentially you know all the participants. You don't just have new people join the network. You have to be permissioned, whereas with the public ones, anyone can join. From the perspective of participants, the public blockchains allow for people to be pseudo-anonymous. So pseudo-anonymous means that you are only represented by an account number, but if you've got the correct amount of, a sufficient amount of policing activity trying to trace who's using that account number, then it's likely to come back to a real world person. And the FBI, for instance, did that with someone who was using Bitcoin at one point. In Consortium, everyone is known, so you know all the participants. So with the blockchains, you want to enforce good behavior. So for instance, you don't want people spamming the network. And public blockchains use something called crypto economics, which essentially means it's economic incentivization to do the right thing and fining you if you're trying to do the wrong thing. So for instance, if you charge per transaction and essentially do surge charging, so similar to how, say, Uber might do surge charging for catching a taxi, this is surge charging. If you want to put a lot of transactions in at once, the transaction costs might go up. And so they use crypto economics to try and make sure that people do the right thing of just putting in a reasonable number of transactions. In a consortium blockchain, you rely on external enforcement. So essentially, if someone starts doing something nefarious, you rely on the fact that you can go to court and have some enforcement against the company that's doing something bad. So other areas of interest are the security properties. So authenticity is all about proving origin, where, who sent that transaction and really identifying which account originated a transaction. So both public and consortium blockchains have that. So access control is limiting which transactions would be processed and maybe which accounts can be used for transactions. So in public blockchains, you can limit which accounts can call solidity contracts from actually implementing that business logic to say, I'm only going to accept transactions from certain accounts. Whereas in consortium networks, you tend to have a lot more access control features. Both have good integrity. Integrity means that you can't alter the state of the blockchain, or you can't alter transactions that are already in. Non-repudiation, that relates to essentially saying, I didn't do something. So say if the Ether price was 50 and then it goes down and I go and buy some and then suddenly it crashes to 2, non-repudiation locks me in and says, hey, you did that transaction. There's no way of you saying you didn't do it. So public blockchains have got very, very good non-repudiation properties. So once something's in there, then it's pretty much rock solid. Whereas consortium blockchains, they tend to have good non-repudiation, but there are caveats with it. And you've got to look at each and every blockchain and probably discuss with someone who's in the field exactly what properties you need and what that chain will give you. Confidentiality is essentially, you can imagine masking or encryption. So something that is going to keep something secret. And so public blockchains, as the name implies, don't have any confidentiality. So the data is encrypted when it's being transmitted between nodes and protected between nodes, but when it's actually in the blockchain or on the distributed ledger, it's all public. So every single value can be seen. In consortium chains, you do have confidentiality, either via limiting who has access to the data or encrypting the data as well. Privacy is related to knowing who's involved in transactions and who the participants are. So in public blockchains, you don't have any of that, whereas in consortium blockchains, you tend to have that feature. And that is around about 15 minutes, and hopefully you've learnt a little bit about blockchain. And the conference, Supply Chain on Blockchain, is going to be on Monday, July the 15th in Brisbane, Australia. Go to that URL to find out more and to get the link to register. Are there any questions?
Thank you, Peter. I have a question. It might look silly, but let's say we have a blockchain in operation, and I'm using the blockchain or whatever money is based on it. And I go to a restaurant and and I want to pay for the food I get there. How many other nodes should actually be engaged to approve my transaction, or how this transaction usually happens?
Okay, that's a great question. So assuming that you've got a wallet on your telephone, an electronic wallet, it is then going to talk to a terminal at the shop, and it'll send off the transaction. And that transaction might go to a node which isn't actually a miner, and then maybe then it gets forwarded to a miner. The miner node will try and put that transaction into its list. So your transaction will get spread across the network. And so all of the miners will end up having it in their list of transactions. But your one will go, say, into a certain miner. That miner will create a block and be, say, the one to win the puzzle problem. And then you will then be able to, so it'll be then in a block. And then depending on the blockchain and the consensus algorithm, you'll have to wait a certain number of blocks before you can be sure that it won't revert, because the idea is you've got a widely distributed network, and so another block might have been minted in another part of the network at exactly the same time. And so you work in Bitcoin, it works on what is the longest block, and in Ethereum it's related to the heaviest block, and heaviest block is related to how many ancestors it's got. And so anyway, you need to wait a little bit of time, and after you've waited, say, I don't know, 10 transactions, or 10 blocks, you can then look at it and say, my transaction is in the blockchain after 10 blocks, so it's never going to be revoked. But you know, you've also got to weigh up as the more blocks are added, the probability of the block being final increases. And so if it's, say, a coffee for $3, then maybe you're happy with 80% probability that it's going to be final. Whereas maybe if it's a $1 million transaction, you want 99.99999% probability. So does that make sense?
And is there any estimate of the time usually it would take, let's say, for usual daily life transactions, how long it would take?
So that's a great question. So if it was, so on Ethereum, your block time's 15 seconds, thereabouts. And if you wanted to wait, say, 10 transactions, that would be 10 times 15 seconds is 2.5 minutes. But then maybe you might think, look, I'm happy to just wait 4 block confirmation, so that would just be 1 minute. It depends on your risk appetite, you know, because I mean, you've got to, if you're the person who's operating, say, the cafe or restaurant, you would need to weigh up how quickly you want to clear transactions compared to your risk appetite. But yeah, so using blockchain for these small payments like this, where they're very time sensitive, is a interesting one. Say, for example, it was a slightly different transaction where you were, say, buying your ticket for the conference using, say, Ether or Bitcoin, then it taking even 5 minutes wouldn't be a problem at all. Whereas, yeah, for something like this, you really do want a small confirmation time.
Hi, Peter. If you allow me to ask a question, first of all, thanks for the interesting clarification on the blockchain. I would like to sort of hear more about a more real-world application where you mentioned the blockchain is like an immutable ledger. It cannot be changed back in time. You can only add to it. So could you explain to us and the viewers a bit, like if, for example, I want to confirm and sign a transaction, for example, I want to buy a house, and let's assume that's on the blockchain, but I also want that my personal identification and a way of signature is both formalized so that I can give my formal, let's say, approval / signature, and at the same time have my citizenry or personal information linked to that transaction because I want that it's coined that I'm the owner of that asset / house.
Yeah, so for something like that, you're really getting into, so if you wanted to have that, you'd need a land registry. Say, the Queensland government would have a land registry, so they would need to have all of their information in a blockchain. And then if you wanted to then maybe have the actual exchange happen online, so in the blockchain, then you probably have to have a separate blockchain maybe, which is specifically related to doing that deal. And so you might have, say, your, so you might put your money, you might say, all right, I'm going to pay, I don't know, $700,000 for a house and I need finance, but I'm only prepared to do it assuming that the various, say, pest inspection and some other inspection has happened. And so though you might have a smart contract, so a bit of that business logic that I've been talking about, where it waits until the person who's going to do the pest inspection confirms that it's all good, and then maybe your bank says, yes, I'm prepared to loan you 500,000, and then you might then transact it, and then the overall result of that might be that the bank gives someone 500,000, you give them 200,000, and then the land registry is updated. And you want all of that, of course, to happen atomically. You want it to happen at exactly the same time. So some of the technology I've described there does exist today, and some of the other bits is actually technology that Sandra Horacio and I are actually working on to allow you to do that cross-chain atomic update.
Wonderful, thank you.
Tanya, what are your thoughts?
Thank you. I've really enjoyed this. It's good. Look, I'm still catching up on blockchain. I've done a bit of research, but not a great deal. That was interesting to me because I was interested in how the motivation works. I can understand it with Ethereum. So when you're talking about crypto economy, that's interesting. As a behavioral motivation, that's interesting to me. I'm still struggling to get my head around the concept, the different concept between a blockchain as a private distributed database and I mean, I can understand that it's distributed as opposed to having a database on a ledger. I'm still trying to get my head around the fundamental application difference that it would mean in, say, supply chain management or cross-border documentation, which is where I'm kind of working and looking at. So I think I'm going to very much be sitting back and listening and learning rather than saying too much, especially at the conference.
Look, so I think you've hit on something which I meant to hit on but failed to. So in this slide here that I've just brought up, one of the things to think about with these different organizations and the different computers is that they might not all trust each other. So you might have various different databases there, and I mean different computers run by different companies, and you can't work out which jurisdiction the database should be in, which company should own it. Having a shared database could be the way to go. And so I guess the thing about as opposed to normal distributed database is that they allow for you to be more attacker resilient, or essentially nefarious actor resilient, and it's got that coming to a consensus far more. Does that make sense?
Absolutely. No, I can absolutely see that. And that, yes, I can see the resilience there, and especially with cross-border things where you're got data crossing borders, crossing countries. Yeah, I'm looking forward to the conference.
Okay, that's brilliant. Thank you.
Thank you.
David, do you have any questions?
No, thanks. Just picking it up on hoping to get to the conference, so and listen to some of these things in practice, because I hear about examples and what have you, but it's similar questions to Tanya or issues. But it was interesting listening to the beef example for the last session, because it sort of opened my eyes about what actually will go on to these chains.
Yep. Yes, I think it's good to have this underlying theory, but having how the rubber meets the road, as it were, the actual use cases is very important. And my hope is that the conference will really help to shake out that.
Good, thank you.
All right, well, thank you everyone for joining. It's been great. It's always great to have an audience and to have real questions at these sorts of webinars. So thank you, and I'll be sharing this on YouTube probably later today. So thank you for joining, and have a great day. Bye-bye.
Bye-bye, everyone.
Thank you.